Welcome to The Explainer. Today, we are diving deep into the world of differential equations. But we're not just sticking to the basics, oh no. We are upgrading our entire mathematical toolkit to tackle some of the most powerful and frankly elegant concepts out there.
All right, here's our game plan. We're going to start with a quick refresher on the basics, just to warm up. Then we'll ask a really deep question about whether solutions even exist in the first place. From there, we'll get into the fun stuff, interconnected systems. And we'll finish up with a true game changer, the Laplace transform. So first things first, let's have a quick look at the essential hand tools in our kit. These are the tried and true methods for first-order differential equations that, every student gets to know and love. These are the absolute workhorses for a reason, right? For separable equations, you just pull the variables apart and integrate. Easy enough. Homogeneous equations, you can use a clever little substitution to make your life easier. And for linear equations, the integrating factor is just this fantastic trick up your sleeve. But as great as these are, they have their limits. They definitely can't solve everything. Now, before we start adding more advanced, heavy-duty tools to our collection, we have to stop and ask a really foundational question. When we're staring down a differential equation, how do we even know for sure that a solution exists? And if we do find one, is it the only one? And this is absolutely crucial. You don't want to be spinning your wheels hunting for something that isn't even there. Or, maybe you find one answer and call it a day when there are actually a bunch of other solutions hiding out. We need to be certain. And that brings us to this really slick technique called Picard's method. It's basically an iterative process. It lets us build a solution piece by piece. You start with a guess, you plug it into the formula, and it refines it, getting you closer and closer to the real deal with every single pass. Let's just watch this thing work its magic. For a simple equation like y equals y, we start with our initial condition. And look, with each iteration, another term gets tacked onto our approximation. You can literally see the power series for e to the x building itself right before your eyes. And what's that? It's the exact solution. It's an amazing way to see that not only does a solution exist, but we can actually construct it from the ground up. Okay, so we've got a way to confirm solutions exist. Great, but now let's wade into some more complex waters. In the real world, problems are rarely neat and tidy and isolated, right? Think about predator-prey populations or complex electrical circuits. These are systems of interconnected equations, and they demand a totally different set of tools. So, on the left, that's our standard differential equation, familiar territory. But look at the system on the right. The rate of change of x1 depends on x2, and the rate of change of x2 depends on both of them. They're all tangled up. Our old single variable tools, well, they just aren't going to cut it here. We need a whole new approach. The solution, it turns out, is to reframe the problem using linear algebra. We can take that whole messy system and represent it with this single, clean, elegant matrix equation. And just by doing that, we've opened up a whole new and much more powerful way to find the solution. And the key to unlocking this matrix equation is finding the eigenvalues and eigenvectors of that matrix A. Now, these aren't just some abstract math concepts. You can think of them as the DNA of the system. They tell you its fundamental behaviors, the natural ways it's going to grow or shrink or even oscillate. And here's the best part. Once you have those eigenvalues, they give you a direct roadmap to the solution. If they're real and different, your solution is going to be a mix of exponential functions. If they're repeated, things get a little more complex. And if your eigenvalues are complex numbers, well, that's a dead giveaway that your system oscillates, and you're going to see sines and cosines pop up in your solution. Okay, now it's time to bring out the big gun. We're about to introduce the most powerful tool in our kit. The Laplace transform is, and I'm not exaggerating, a revolutionary method that will completely change how you think about solving differential equations. Seriously, just think about that for a second. What if you could take a nasty-looking differential equation with all its derivatives and integrals and just turn it into a simple algebra problem? Well, that's exactly the promise of the Laplace transform. This integral right here is the engine of the whole thing. It takes a function from the familiar world of time, we'll call it the t-domain, and zaps it into a whole new world, the s-domain. And in this new domain, the rules are different, and the problems get a whole lot simpler. This table is where you really see the magic. It's like a translation dictionary. A simple constant in the time world becomes 1 over s. An exponential becomes a simple fraction. Even tricky oscillating functions like sine and cosine get turned into these really straightforward rational functions.
We are literally swapping calculus for basic algebra. So, we've got our new power tool. Let's fire it up and see what it can do. You're about to see just how ridiculously straightforward solving complex DEs can become. This is the secret sauce. This is the whole reason it works. The Laplace transform turns the act of taking a derivative, the very heart of a differential equation, into simple multiplication by s. The calculus just vanishes, and we're left with an algebra problem that even has our initial conditions baked right in.
The process itself is just so elegant. It's a simple three-step dance. Step 1, transform the whole differential equation into the s domain. Step 2, solve the new algebraic equation for y of s. This is the easy part. And finally, step 3, use your transform dictionary in reverse to convert back to the t domain and get your solution, y of t. Done. This quote just sums it up perfectly. The Laplace transform is a bridge to a simpler mathematical world. And this is exactly why engineers absolutely love this tool. It can handle problems with things like discontinuous inputs, like flipping a switch in a circuit, which are a total nightmare to model any other way. So, as we wrap up here, I want you to remember that these tools we've looked at today, they're about so much more than just solving equations. They're about the power of perspective. It shows us that by learning to reframe a problem, whether that's with a matrix or a transform, we can often find a much simpler path to the solution, turning what looked like an intimidating challenge into something totally manageable.